In this module, we overview gas properties that are used to describe gases in physics and chemistry and introduce the concepts of ideal gas and the ideal gas law. This module will also introduce you to the concept of the equation of state using the ideal gas law as an example. When we discuss the state of a gas, we characterize it by quantifying certain properties known as physical quantities. These properties are parameters that describe the physical state of the gas. The amount of substance or the number of moles denoted by N quantifies the number of particles in the given amount of gas. The volume denoted by V represents the space occupied by the gas. Pressure denoted by P is the force exerted by the gas on the container walls, which is expressed per unit of area. The temperature denoted by T is a complex thermodynamic concept, but it can be simplified as a measure of the average kinetic energy of the gas particles. Together, these four parameters provide an unambiguous description of the state of a gas. Historically, the physical state of gases was first studied by investigating the connections between different pairs of these properties, while the other two parameters were kept constant. As a result, multiple gas laws were formulated. Avogadro's law states that equal volumes of all gases contain the same number of particles at the same pressure and temperature. Two slightly different statements follow from this law. First, it implies that for a given pressure and temperature, the volume occupied by the gas and the number of gas particles are directly proportional to each other. If we double the volume, we double the number of particles. This allows us to introduce the ratio between them, the molar volume, as another physical quantity describing the state of the gas. Second, it implies that it does not matter which gas exactly we are considering, they all have the same number of particles in equal volume and therefore the same molar volume if the pressure and the temperature are the same. Mathematically, we can express it with a statement that the molar volume is a function of the pressure and the temperature only and is independent of the amount and nature of the considered gas. Very often we are only interested in the general physical state of the gas without referring to its specific amount. In this case, it follows from Avogadro's law that we need only three intensive parameters: pressure, temperature, and molar volume to describe the state of any gas independently of the exact amount. Another historical gas law, the Boyle-Mariotte law, states that the pressure exerted by a gas is inversely proportional to the volume it occupies if the temperature and the amount of gas remain unchanged. This means we consider a closed system with a constant amount of gas under isothermal conditions. Mathematically, these conditions can be formulated as N and T being constant. The Boyle-Mariotte law can be described by the equation P is inversely proportional to V, P times V equals a constant, and P1 times V1 is equal to P2 times V2, where P1 and P2 and V1 and V2 refer to the pressure and volume of two states of the ideal gas. Here, the left figure depicts the variation of the pressure of a sample of gas as the volume changes. Each of the curves in the graph corresponds to a single temperature, hence called an isotherm. According to Boyle's law, the isotherms of gases are hyperbolas. An alternative depiction, shown on the right, is a plot of pressure against 1 over volume. In this plot, the isotherms are straight lines because P is proportional to 1 over V. Note that all the lines extrapolate to the point P equal to 0, 1 over V equal to 0, but have slopes that depend on the temperature. Charles' law declares that the volume of a gas is directly proportional to its absolute thermodynamic temperature when both the pressure and the amount of the gas are held constant. These conditions refer to a closed system operating under isobaric conditions. N and P are constant. Charles' law can be represented mathematically in several ways. V is directly proportional to T, V over T equals a constant, and V1 over T1 is equal to V2 over T2, where 1 and 2 refer to two different states of the ideal gas. This figure illustrates the linear relationship between volume and absolute temperature as formulated by Charles' law. Each line in the graph corresponds to a specific constant pressure. Consequently, they are called isobars. An essential property to note is that all isobars extrapolate towards a common point, where the volume V is 0 and the temperature T is also 0. The slope of these isobars increases when the pressure decreases. Another partial gas law, which seems to be also called Charles' law, looks exactly like the previously described Charles' law, except that we swap volume and pressure. It states that the pressure of a gas is proportional to its absolute thermodynamic temperature when the volume and the amount of the gas are constant. These conditions refer to a closed system under isochoric conditions. N and V are constant. It can be represented as P is proportional to T, P over T equals a constant, and P1 over T1 is equal to P2 over T2. This figure illustrates the corresponding linear relationship between pressure and absolute temperature. The lines in the graph correspond to a specific volume and are called isochores. All isochores extrapolate towards a point of zero pressure and zero absolute temperature. The slope of the isochores increases when the volume decreases. Building on what we have already discussed, we can integrate the empirical observations we have gathered from Avogadro's principle and gas laws into a single unified expression. P times V equals a constant multiplied by N times T. A key to the combined gas law is now the constant of proportionality. Experimental results have shown that this constant remains unchanged for all gases. This constant is denoted by the symbol R and referred to as the ideal, molar, or universal gas constant. Now, using this constant, we can formulate the equation known as the ideal or perfect gas law. Pressure times volume equals the number of moles times the universal gas constant times the absolute temperature. We can also disregard the specific amount of gas and formulate the ideal gas law using only three intensive variables. Pressure times molar volume equals the universal gas constant times the absolute temperature. The value of the universal gas constant R was originally determined experimentally. However, R is also defined as the Avogadro constant and A multiplied by the Boltzmann constant Kb. Since the 2019 redefinition of SI base units, both Na and Kb are defined with exact numerical values when expressed in SI units. As a consequence, the SI value of the universal gas constant is now not an experimental, but rather an exact, predefined value. One way or another, the value of R is 8.314 joules per Kelvin per mole. When a gas follows this law exactly under any given condition, we label it as an ideal or perfect gas. Such ideal gas is rather a theoretical model than an actual physical object. For any actual gas, which we will refer to as a real gas, the ideal gas law is only an approximation. It doesn't describe the behavior of real gases under every condition. However, the approximation of using the ideal gas law for real gases becomes increasingly accurate as the pressure of the gas decreases and approaches zero. Now we will turn to a very important concept of thermodynamics, the equations of state. For any pure substance, its state is, in principle, defined by four variables: the amount of substance N, the volume V, the pressure P, and the temperature T. However, various experimental studies have established that out of these four, only three can be varied independently. That means, if we know the values of any three of these variables, the fourth one becomes predetermined. What binds these variables together? The answer is the equation of state. This is understood as a thermodynamic equation relating state variables. For most substances, the general form of the equation of state can be expressed as P being a function of T, V, and N. This means that if we know the temperature, volume, and the number of moles of a substance, the pressure is determined. Note that we can in fact choose any three variables as independent ones and consider the remaining variable as a dependent one. Each substance, based on its inherent properties, can be described by its own equation of state, although the explicit form of the equation is known in only a few special cases. One example of the equation of state that stands out is the ideal gas law. Why do we emphasize the ideal gas law in our course? For the following reasons. It has a simple form that ensures easy understanding and computations. It provides an accurate description of a multitude of gases across a wide range of parameters. One of the key advantages is its generality. It doesn't require any substance-specific parameters, making it universal in its application. Finally, given its importance and relevance, we will be frequently referring to and using the ideal gas law throughout our physical chemistry course. Upon closer examination, the ideal gas law as an equation of state fundamentally connects three variables. Thus, it can be visually represented as a surface in a three-dimensional space. The axes that define the space are temperature, pressure, and volume. Since volume is an extensive variable, it implies a volume for a constant amount of gas. Alternatively, we can use molar volume as an intensive variable independent of the amount of gas. This modification won't alter the appearance of the figure. This surface is now a plot of the ideal gas law. Here, the value of one variable is calculated as a function of two other variables. We will use the ideal gas law to highlight general properties of the equations of state. It is often said that the surface representing the equation of state in three-dimensional space illustrates possible states of the system. However, a more accurate formulation would be the equation of state, and thus the surface that represents this equation defines all possible equilibrium states of the considered system. Why is that the case? Theoretically, one could argue that a system, in this instance an ideal gas, can assume any possible state, meaning it can be located at any point within this space. However, if the system does not adhere to the state equation, it is not in equilibrium and must change its state. Given that gas molecules move rapidly with minimal obstruction, a new equilibrium state is established swiftly. This isn't always the case. For example, solid substances might stay in a non-equilibrium state for an extended period. Now let's examine the surface in detail and explore how it relates to the previously studied gas laws. If we section the surface with planes corresponding to a constant temperature, at the intersections we obtain curves representing states of equal temperature. These are the isotherms. By taking sections at constant pressure, we identify lines that represent states with the same pressure, the isobars. Sections taken at constant volume yield lines representing states of constant volume, which we have named isochores. What we would like to show by that is that the isobars, isochores, and isotherms are not standalone constructs. Rather, they are components of the broader equation of state that can be visualized collectively in three-dimensional space. Previously, we spoke about the empirical gas law. The term empirical means that these laws originated from experimental observations. However, the ideal gas law is not solely based on experiments. There is also a theoretical perspective, which offers an elegant and relatively simple derivation of the ideal gas law. It can be derived from a basic model representation of what we can call a theoretical ideal gas as opposed to an experimental ideal gas, approximating real gases in the analysis of experimental results. At its core, theoretical ideal gas is an idealized representation of real gases. The theoretical model represents the ideal gas as multiple, randomly moving, indistinguishable particles. These particles don't have any volume of their own. They are considered point particles. The only interactions they experience are hard, elastic collisions with each other and the walls containing them. Very importantly, these particles don't experience any attractive or repulsive forces apart from these point-like collisions. The model and the concept of ideal gas have been invaluable for scientific explorations, especially in statistical mechanics. From the way it is formulated, it is clear that any dilute gas, the one with the average distance between molecules being much larger than the size of the molecules, comes very close to the ideal gas. The ideal gas model gives rise to the theoretical derivation of the ideal gas law, a simplified equation of state. Historically, this approach and derivation were established in the 19th century. It remains relevant today because of its simplicity and the powerful insights it offers. Using minimal assumptions, it draws robust, quantitative conclusions about real gases in a wide range of conditions. To finalize this module, we would like to discuss a couple of things about mixtures of ideal gases. In a mixture of ideal gases, each gas, denoted by I, is characterized by its partial pressure, Pi. The partial pressure of a gas represents the pressure that a specific gas would exert if it were alone in the entire volume of the original mixture at the same temperature. An empirical rule known as Dalton's law states that the total pressure exerted by a mixture of gases is the sum of the pressures that each one would exert if it occupied the container alone, the latter meaning partial pressure. Mathematically, we can write it as the total pressure P is equal to the sum over all I of the partial pressures Pi. Strictly speaking, this law is valid only for mixtures of ideal gases. A significant interaction between molecules of different real gases can change the pressure exerted by them substantially. The mole fraction of an individual gas I in the mixture Xi is, of course, the ratio of the number of moles of a particular gas I to the total number of moles in the gas mixture N. At the same time, it is also equivalent to the ratio of its partial pressure to the total pressure of the mixture. This relation is often used when considering mixtures of ideal gases.